Welcome back, 8th graders, to another explainer. Today, we're jumping right into one of the absolutely coolest concepts in geometry, transformation. We're going to unlock the mathematical secrets behind how things grow, shrink, and, most importantly, maintain their true identity through it all. So grab your notebooks and let's dive into faithful scales, the geometry of dilations and similarity.
Now, you might be wondering, how do we actually resize our world without losing its essential shape? Think about it for a sec. Have you ever tried to resize a photo on your phone? And maybe you dragged the wrong corner? And then suddenly, boom, your best friend's face is stretched super wide or squished completely flat. It looks totally ridiculous, right? So how do we resize our world, whether we're talking about a photo, a map, or even a building, without losing its core shape? How do we keep things absolutely perfect, just bigger or smaller?
Okay, let's dive into this, because honestly, this isn't just a math problem. The source material frames it as a really profound life principle, too. In math, understanding scale and proportion trains your brain to think relationally. It helps you see how a tiny detail perfectly reflects the whole picture. The curriculum connects this to a verse from Luke 16:10. Whoever can be trusted with very little can also be trusted with much. The idea presented here is that being faithful in the small, precise details is exactly the same skill as managing the really big, massive things. Moving on to Section 1, the power of resizing, seeing math in the real world.
Let's start by laying down our golden definition for the day. A dilation is a transformation that changes the size of a figure, but absolutely not its shape. I really want you to underline that in your mind. The underlying shape remains perfectly, flawlessly intact. The angles, they stay the same. The proportions, exactly the same. The figure literally just gets bigger or it gets smaller. So why does this matter in the real world? Well, because dilations pretty much run our modern world. When a doctor zooms in on a medical scan to catch a tiny life-saving detail, they're using dilations. When an architect creates a flat blueprint design that will eventually become a towering skyscraper, yep, that's a dilation too. From photography and the video game animations you play, right down to the scale drawings you make in art class, none of it actually works without the math of faithful, accurate resizing.
All right, Section 2, discovering scale factors, the rules of transformation. Now, what's really interesting about this is the secret mathematical code to precision resizing. We call this the scale factor, and it's basically just the multiplier we use. There are only 3 simple rules to remember here. If your scale factor is greater than 1, you get an enlargement. The figure grows. If your scale factor is less than 1, like a fraction or a decimal, you get a reduction, meaning the figure shrinks. And if your scale factor is exactly 1, well, multiplying by 1 changes nothing, so your figure stays exactly the same size. No change at all. As you'll see here, on the left, we have enlargement, where a figure is growing proportionally. And over on the right, we have a reduction, where it's shrinking proportionally. The big contrast here is simply size, making things bigger versus making them smaller. But in both cases, and this is absolutely crucial, the essence of the shape, its core mathematical DNA, does not change one bit. Okay, Section 3, let's do the math, applying scale factors. Let's move to the practical side and see how this builds. It is time to actually apply our scale factors, and I promise you, the mechanics of this are a breeze. It literally just takes 2 steps. Step 1, look at your original coordinate pair on the graph, your x and your y. Step 2, multiply each of those numbers by the given scale factor. That is the whole shebang. Seriously, if you can do basic multiplication, you are going to master geometric dilations in no time. Let's try it out. Here is our first scale factor, the number 2. Now, think back to our rules for a second. Is 2 greater than 1 or less than 1? Right, it's greater than 1, so we already know, before we even touch a calculator or do any math, that we are going to create an enlargement. So, here is example 1. We want to dilate the coordinate pair 3, 4 with our scale factor of 2. We just take our x value, which is 3, and multiply it by 2. That gives us 6. Then we take our y value, which is 4, and multiply that by 2. That gives us 8. Boom! Our new coordinate is 6, 8. The math is really that simple, and it works perfectly every single time. Okay, let's look at our next scale factor. It's 0.5. I want you to do a quick mental check right now. Based on the rules we just went over, will multiplying by 0.5 create an enlargement or a reduction? Well, if you said reduction, you hit the nail on the head. And this brilliantly illustrates how the math behaves. In example 2, we have the coordinate 10, 8. We multiplied 10 by our scale factor of 0.5, giving us 5. We multiply 8 by zero point 0.5, giving us 4. Multiplying by 0.5 perfectly halves our original figure, smoothly bringing our new point to 5, 4. But what if you're just looking at two shapes, and you need to figure out if one is a true dilation of the other? Well, we run a similarity check. For two figures, say two triangles, to be completely mathematically similar, they have to meet two exact structural conditions. First, their corresponding angle measures must be exactly equal, no exceptions. Second, all of their corresponding sides must be perfectly proportional. If those two things are true, congratulations, you're looking at similar figures.
Which brings us to Section 4, your turn to practice, the homework challenge.
Now, don't groan. This really isn't a chore. It's just an awesome opportunity to prove your new math superpowers. You've got 5 quick challenges here. Numbers 1 and 2 are just practicing exactly what we just did, multiplying your coordinates by the scale factors 3 and then 0.5. Number 3 is a fantastic test of that similarity check we literally just talked about. Look really closely at how the sides 3, 4, and 5 relate to 6, 8, and 10. Number 4 is kind of like a fun puzzle where you have to work backwards to find the multiplier. And for number 5, you just need to describe what happens when you dilate a rectangle by 0.25. You guys are going to absolutely crush this. Moving into Section 5, Transformation and True Character. The essence remains. I want us to slow down the pacing for a moment here, because the curriculum draws a really interesting parallel between geometry and personal character. On the left, with geometric transformation, a figure's appearance might get way bigger or way smaller, but its core shape, its true essence, stays exactly the same. And on the right, the text compares this to spiritual transformation. The idea is that as people grow, their hearts change and their circumstances change, but their core spiritual identity stays exactly the same. The reality is, life is going to dilate you. You're gonna face situations that stretch you into completely new directions, or situations that might make you feel small and reduced. But just like transformations change how a figure appears but not its essence, the text encourages you to stay true to your core identity. The text encourages you to let your growth be guided by integrity, just as this math requires structure and perfect order to actually work. Finally, Section 6, Education, Morality, and Peace, the HeroesMartAcademy philosophy. This philosophy is basically the heartbeat of the HeroesMartAcademy's Godly Learners series. They intertwine their educational lessons with moral teachings for one very stark, very real reason, which is stated as, education without morality will hurt. I mean, think about it from their perspective. What is the actual point of being incredibly smart, of knowing all the math and science in the world, if we continue to make bad choices that hurt ourselves and the people around us? Knowledge without character can actually be a pretty dangerous thing. But on the flip side, the material suggests that when learning is combined with strong character, there's a promise involved. The slide highlights Romans 8:6-7, discussing the promise of peace of mind. The ultimate takeaway from the Academy here is that when you intertwine your hard work and education with a strong moral compass, real, lasting peace of mind becomes your actual everyday experience. And that brings us to our final thought for this explainer. You now have the mathematical tools to faithfully resize and transform the shapes in your world. But the curriculum also asks you to consider the moral tools you have to transform your life. So you have to ask yourself, how will you apply this peace of mind and this steadfast integrity to your own life today? Reflect on that as you tackle your math homework and keep looking for the cool ways that math and character perfectly align. Thanks so much for joining me on this explainer, and I will see you next time.